Last class, we left off with this limit definition of the definite integral. And we said the basic idea of this is that we're going to take rectangles and approximate the area under the curve by using more and more rectangles that get more and more accurate to white, or more and more like what's underneath the curve, right? As the width of these rectangles go to 0, the accuracy for the area of all the rectangles will approach the area under the curve. So just some points about what all of these, the different values of what x sub n can be. We have the left-hand sum, which is saying, let me draw this on the board. Okay, so if the rectangles that we use to approximate the area under the curve are built so that the left side of every rectangle is equal to the height of our function here, then this is a left-hand sum. If, on the other hand, the right side is equal to the function, it's a right-hand sum. And if the middle is equal to the height of our function, it's the midpoint sum. So what we're doing here is we're saying this is delta x, and this is f x star n. So the area of the nth rectangle is equal to f x star n times delta delta x. In this case, x star n is equal to a plus n delta x. And this is starting with n at 0. So the area then, I'll come back to that in a second. On this case, or in this case, like I said, this is the right-hand sum. Again, the width is delta x. The height of our rectangle, fx star n, is going to be determined by the right side of the rectangle, right? And it's going to be set equal to the height of the function. So here we have x n star is equal to an, or my mistake, a plus n plus 1 delta x. And again, delta x. This time we're using the midpoint. Which is going to be a plus plus 1/2 delta x. So the three most common different ways of approximating these, right? Of building our rectangles. Now, let me clean this up just a little bit on the board. Xn star is equal to a plus a delta x. And this is all indexed, assuming that A is approximately equal to the sum from n equal to 0 to k minus 1 f xn star delta x. Again, like I've said before, indexing changes here a lot. We can index this from 0 to k minus 1. That's going to be k number of rectangles, right? Because the first rectangle is the 0th rectangle. So the kth rectangle would be k minus 1, right? Makes sense what I mean? Having said that, if we change these indexes, we have to change what these n values are. So if we index it from n equal to 1 up to k, this would change by subtracting 1. Makes sense what I mean? So, having said all of this, the basic idea, again, is just that we're going to say, let's take these rectangles, make them really small, add a bunch of them up. In the limit, this gives us the definite integral. Yeah. But if we unimpose the limit, then this thing just approximates the area, right? So we don't necessarily need to use calculus to get the area or something close to the area underneath the curve. We could just use algebra, calculate these fxn values times delta x and add them together. That's just algebra, right? So as an example, we're going to look at first the function f of x is equal to negative x squared plus 5. We're going to integrate it, or we're going to get the area between 0 and 2. We're going to use 5 rectangles. All right. And what else are we going to do? Doesn't say anything else here. Here we're going to use the midpoint. I don't think they actually state that in the problem, do they? No, they don't. Okay. Yeah, the way this problem is set up, we're going to be using the midpoint. So, first thing we need to do is just consider what the picture is even going to end up looking like, right? We've got the function negative x squared plus 5. We're trying to find the area from 0 to 2. We're going to break up our interval into 5 subintervals. Then we're going to take and build rectangles that are the height of the midpoint of each of those subintervals. height of the function at, I should say, the midpoint of each of those subintervals. We're going to find those areas and down we go. Before we do anything else, though, I want to point out, check out what's happening when we use these midpoints. We have a little bit of underestimation here, 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 and a little bit of overestimation here, here, and here, here, right? So the reason why this is going to be really accurate is because those overestimations and underestimations are going to start to wash out over time, right? Smaller and smaller rectangles means the over and under will be smaller and smaller. But what we're about to see is that even for 5 rectangles, this is going to be pretty damn close, actually. So how does this all work? What are we doing here? We're writing this in our notation. First thing we need to do is find out what delta x is. Delta x, we know, is b minus a divided by the number of rectangles, right? In our case, this is 5. B is going to be 2. A is going to be 0. Divide 5. Delta x is 2/5. Yeah? Okay. Now, a minute ago, I said we're going to use the midpoint rule. Midpoint rule is a plus n plus 1/2 delta x well, a is 0 here, right? And n, that just depends on which rectangle we're looking at. Delta x, we just said, is 2/5. So this is equal to n plus 1/2 2/5. So putting all of this together in notation, this is going to look like the sum from n equal to 0 to 5 minus 1 of f of n plus 1, or I mean n plus 1/2 times delta x, this times delta x, right? So just so I can show where all of this comes from, how we got to it. N is equal to 0, f of x n star, delta x. This is going to be n equal to 0, up 2, 4, f of plus 1/2 2/x, or 2/5, I mean, times 2/5. Yeah? Everybody agree? Folks at home, is this making sense so far?
Yeah.
Yeah, awesome. All right, so this is just what it looks like in condensed notation. I'm writing it this way just because it's sometimes nicer to use this notation when we're trying to work out a problem than it is just to have everything calculated out every single time, right? But this sets up the rules for us to figure out what we're going to do next. Does that make sense what I mean? Yeah. All right. So what this is saying then is that we're going to take f, n is going to start at 0, 0 plus 1/2 times 2 over 5. This whole thing times 2 over 5. Then we're going to add f, n is going to be 1 now, plus 1/2 times 2 over 5, that quantity times 2 over 5. Now we're going to have at 2, right? And it's going to be 2 now, plus 1/2, 2 over 5, 2 over 5, plus f. This is long, I know. I'm sorry that it is long. 2 over 5, 2 over 5, and finally, plus f, n is now equal to 4, plus 1/2, 2 over 5, 2 over 5. Holy hell, that's a lot, right? So what's happening here? What's changing is that n value each time, right? Started off at 0, then we moved to 1, 2, 3, and finally 4. So everything stays the same. We just changed what the n value is, right? But notice what we can do here. We've got this factor of 2 over 5 in each term. So to make this easier on ourselves, we could pull out 2 over 5. Calculate our functions at each of these values now. Which I'm not going to write in this long, ridiculous notation this time. I'm going to write it as x 0 star plus f x star plus f x star again plus f x star plus f star 0, 1, 2, 3, and 4. So now we can factor out, like I said, that 2 over 5 and just look at calculating our function at each of those x star values, right? At each of those midpoint values. So once we take the sum of our function at the midpoints, and then we can multiply by 2 over 5 to get the answer. Everybody cool with this? So the point here is that we can really reduce the legwork of some of this just by factoring out and doing that multiplication later. This is ugly, I know. It's tedious and time consuming. There's a slightly quicker process, I think, that the book uses. Instead of going through and identifying the notation and writing it in shorthand like this, they just say, all right, find your sub-intervals. If you're using the midpoint, find the midpoint. Then just write everything out, do the calculations, factor out that 2 over 5, and solve. So the book, they don't show the notation here. And this is the part that I think is confusing. Like, what are we doing here? I think it helps to see this and then to see this side by side. That way we know, okay, what they're saying is, get these subintervals, find your midpoint. That's our xm star in this case, right? Your delta x's, that's the length of each of these intervals, right? And then add everything up, multiply accordingly. So we kind of went about it a little extra just because I wanted to put in this notation for us to see first. Having said that, the general process of applying the midpoint rule. First, find your delta x. It's going to help if you break up your interval into subintervals right away. So you're going to say, all right, starting at A, adding delta x, that's my first interval. The next delta x is my second interval, so forth and so on. Then find the midpoints, then approximate, right? And that's what we found in this problem. I'm going to go back and make a point about this. This final value here is only an approximation, but it's a pretty good one, actually. So just to show how good of an approximation it is, our 5 rectangles got 7.36 to be the approximated area, right? The actual area is supposed to be 22/3, so 7.3 repeating. We're within 0.03 of the actual answer. That's pretty damn close, actually. I mean, that's 100th of a unit, right? So we're pretty close. That's just using 5 rectangles. If we took it out to 10 rectangles, we're within 1/100th of the solution. We're actually less than 1/100th of the solution away. 15, we're within 1/1000th, or 3/1000ths. 20, 25, 30, these are getting really close, but really they don't get close that fast over time. That's why we can stop at 5 intervals and say this is good enough, because we only gain, what, 0.02 digits in accuracy? Like that's not really helpful. And it takes 30 digits, 30 subintervals to get within 1/1000th of accuracy. So 5 rectangles, that's pretty decent. Does this make sense? What I mean? Yep. Cool. Okay. So, as another example, and I actually really like this example because it lets me explain why we're even doing this. Consider this integral. Consider this definite integral where our function is the inverse of x squared plus 1. How would you integrate that? First thought we might have looking at it is, this might be the power rule. But the power rule doesn't quite apply here, does it? Okay, what about with u sub? Our u here would maybe be x. So du would be 2x dx, but we don't have another x to work with. So u sub in the power rule doesn't work here. What about the ln? We can rewrite this as the integral of x squared plus 1 to the negative first power dx. Okay, let's try the ln. But the ln doesn't work. Maybe with u sub. Our u then would be x squared plus 1, right? But that still means du dx would be 2x dx. So we don't have a way of integrating this, at least not yet. So if we want to find this, which I am going to go ahead and claim now is pi over 4. I'm going to calculate this. I'm going to need an approximation method. The fact of the matter is, as much as people would love to think that mathematicians know how to solve every problem, that mathematics is complete, why do we even study this stuff as mathematicians? Because it does seem like it ought to be complete, right? Like, what are the questions left? Well, there are a ass ton, I mean like a metric shit ton of functions that we can't integrate. This one we actually can, and it's using properties that we might see by the end of the semester. I don't think we go into any of the trig substitution methods, but if we do, that's where the solution to this exists. And that's why we have pi in here. But without knowing these other integration techniques, to solve this problem, we're going to have to use an approximation method. So again, setting n equal to 5, breaking up our interval, finding our midpoints. We've got our delta x, right? We're just doing that calculation. Here we're saying that integration is approximately equal to that series, right? The sum that we would normally draw. This is our function evaluated at 1 over 10, 3 over 10, 5 over 10, 7 over 10, 9 over 10. All multiplied by 1 over 5. And it comes out to be approximately 0.786. So, again, pi over 4 is the actual answer. So approximately 0.785. Check it out. We're only off by 0.001 now. So we're within 3 decimal places of our answer. That's pretty decent precision given that we only use 5 rectangles. So we are definitely not going to do this problem because it's n is equal to 10. But as another example, we might consider the integral from 1 to 3 of the square root x squared plus 1 dx. Can we integrate that with our current methods? That's almost certainly power rule, right? Because we can rewrite this as 1 over 3 x squared plus 1 to 1/2 dx. So power rule in u sub looks like the most obvious candidate, right? But u then would be x squared plus 1. So du would be 2x dx. We're missing that 2x again. No dice. So, kind of just stuck up Schitt's Creek. You're going to have to approximate this. Using 10 rectangles, what our problem physically looks like is 10 rectangles whose mid value is equal to the height of the function, or whose height is equal to the function at the midpoint of our rectangle on that interval. We're going to take the sum of all of this. Let's get it approximated. So the whole process, find our subintervals and then the midpoints of these subintervals. We find our delta x, it's 1/5. Then we plug in the midpoints into our function, add all those together, multiply by 1/5. So that's our delta x. And the answer comes out to be about 4.504. The actual answer, though, to our integral is 4.505, approximately. And it actually looks like this. The reason why they're approximating it here is because these ln's don't have, actually none of these have nice rational values. Square root of 10 doesn't come out to be a terminating decimal. The ln's don't come out to be terminating decimals, and the square root of 2 don't. So these are just really ugly decimal values, and that's why they're approximating it as 4.505. But notice it took us 10 rectangles here to get to 1/1000th precision, right? So different functions will be accurate in different ways. But in general, 5 out of 10 rectangles, that's not a whole lot of calculations as much as it might sound like it is, right? These are getting pretty close pretty quick. From this point on, they kind of die off and they don't get closer very quickly. They don't add precision particularly quick from this point on, is what I mean to say. So we're pretty decent here. Make sense what I mean? So, wrapping all of this up in a nice clean package, this brings us back to that idea of the limit definition of the definite integral. The definite integral can be thought of as the limit of the sum of the area of rectangles as their width goes to 0. Make sense what I mean? So we have the approximation, and then we have the exact solution. So let's take a minute to appreciate this. What we just saw from all of this we've got the limit, as delta x goes to 0, the sum, there's a typo on this slide. Okay. Coming back to this limit definition. One way we can interpret this is that since delta x has to go to 0, that means k has to go to infinity. That means you're adding up an infinite number of values and getting a finite value back. You just added up an infinity of things and got a number back. The implications of this is that this is just a side note to all of this. You could take and add up an infinite number of numbers and get a defined number back. That is insane. When you think about the way numbers act, right? 0.1 plus 0.1 plus 0.1 1,000 times, that goes to infinity. But somehow over here, something's happening in the math that lets this go to a well-defined number. And just as an example of how sensitive this actually is, this diverges to infinity. But this converges. What? That's actually insane. And not just that. Then we have things like 2 to the negative n, that goes to 1. My mistake, that goes to 2. Right? So, just as something cool that's happening under the hood here, you're adding up an infinite number of values to get this. That is an insane idea. Having said that, we've got 13 minutes left. And I think we just hit the end of this. No, not quite. Okay. One last example of an integral we can't solve. The integral and this is probably one of the most important examples you'll see in this entire class. This affects every aspect of your life. This one integral does. The integral from 0 to 1, e to the negative x squared dx. I should actually say this function does. Does anybody recognize this function? People at home, do y'all recognize this function? I bet if I drew its graph, you would. The bell curve. This is the graph of the bell curve. And without using some really heady tricks, there is no way to integrate this. U sub doesn't work. Method we're going to learn in next class, integration by parts, doesn't work. Nothing works. You have to use some really heady tricks to get out the answer. But in the meantime, what does work is approximation methods. That's what we did for the longest time. So why is this important? Well, there's two things. One, we just saw that we can add up an infinite number of things and get a defined value back. That's mind-blowing. The second reason why all of this is important is because there are some functions that apply to every aspect of our lives, like e to the negative x squared, that we need to know its integrations. And we can't necessarily solve these problems without using some form of an approximation method. Having said that, why is this function particularly important other than because it's applied to probability and statistics? Right now, this shows up everywhere with COVID. I mean, we're talking about probabilities and statistics. Anyone who's gotten their jab yet, there had to be some sort of an analysis done on the efficiency and effectiveness of the vaccines using this particular function. So, having said that, I will get off my soapbox and let y'all go for the day. If y'all have any questions, I will stick around.